I want to talk about applications of the group action machinery we've seen to the study of P groups. Okay, let me start with what a P group is. Let's say that P is a prime. A group G in which every element has order P to the K for some K is called a P group. So what is a P group? Every element has order equal to a power of P. When G is finite, this is the same thing as saying that the order of G is equal to a power of P. But there are infinite P groups. So there are infinite groups where every element has finite order. And if all of those finite orders are powers of P, you get an infinite P group. So just to give an example, the unit circle in the complex plane is a group under multiplication. And you can take the subgroup of the unit circle consisting of the union of all the P to the Kth roots of unity for all K. So it contains elements of arbitrarily large P power order, but they all have finite order. More concretely, you can write this as the set of e to the 2 pi I m over P to the n, where n can be any integer that's greater than or equal to 1, and m ranges over 0 to n minus 1. So it's a nice exercise to show that that's actually a subgroup, but this is an infinite P group. Okay, but we'll forget about that now and just talk about finite P groups. So this theorem is often called the fixed point congruence, and it ends up being really helpful. So it gets used in a lot of things. Let's say that G is a finite P group acting on a finite set X. Then the size of X is congruent to the number of fixed points of this action modulo P. So this is something that's true for any finite group acting on, any finite P group acting on a finite set. What we're going to see is that when we make a particular choice of what X is and what the action is, we're going to get interesting consequences. Okay, so the idea builds off something that we did last time. Let's take representatives x1 up through xt for the different orbits. Then, we talked about this last time, the size of x is equal to a sum over the distinct orbits of the size of the orbit. So what is that saying? That's exactly saying that the orbits form a partition of x. Right? So we haven't used anything here. And now using the orbit stabilizer theorem, we see that that's the same as a sum from I equals 1 to t of the index of the stabilizer of xi in G. And now, the order of G is a power of P, let's say P to the m. And we know by Lagrange's theorem that the stabilizer of xi is a subgroup of G. So its index is equal to the size of G divided by the size of this subgroup. So in particular, that index always divides the order of G. But the order of G is a power of a prime. So this index is either 1, which is exactly what it means for xi to be a fixed point, that its stabilizer is the whole group. Or if it's not 1, it's p to some power, where that power is at least 1. So in particular, it's congruent to 0 mod p. So now, if you just take this equation and you reduce it modulo p, what you get is exactly this congruence, that every number on the right-hand side here is either 1 when you have a fixed point, or it's 0 modulo p. So I'll pause and erase, and I'll write down that last little piece of the argument formally. Just to fill in the details of the very last piece of this argument, we conclude that you take this formula, the size of x is the sum over these representatives of the index of the stabilizer of xi in G, and the fact that each one of these indices is either 1 when you get a fixed point, or it's a power of p that's at least p. So it's 0 modulo p. So you take this, reduce it mod p, every non-fixed point xi contributes 0 here in this index mod p, and you just get this size of x is congruent to the number of fixed points modulo p. Okay, so what really happened in this argument is the orbit stabilizer theorem allows us to write the size of x in terms of the sum of a bunch of numbers that divide the order of g. So if the order of g is a prime power, you can say something very strong about the set of numbers that divide the order of g. Okay, so just to make this really concrete, here are two corollaries. If G is the same setup, so a finite P group acting on a finite set X, if P does not divide X, the size of X, then this left-hand side is not 0 mod P. So this right-hand side can't be 0 mod P either. So what does that mean? If the number of fixed points modulo P is not 0, then the number of fixed points is not 0. So there is at least one fixed point. Okay. So if P does divide the size of X, then the number of fixed points mod P is congruent to 0 mod P because the size of X is 0 mod P. It's possible that you have no fixed points at all, but the number of fixed points is congruent to 0 mod P. So if you have 1, then you have at least P. So I'm going to pause and erase and talk about some additional consequences of this result. Let's suppose that G is a non-trivial finite P group. Then P divides the size of the center of G. In particular, the identity element is always in the center, so the size is at least 1. So if P divides it, it's at least P. So what is the proof? Let's just take that fixed point congruence and let G act on itself by conjugation. The fixed points are exactly the elements of the center. We've seen this in an earlier lecture. So what does that mean? The size of the center is congruent to 0 modulo P. We can prove something a little bit stronger with almost no extra effort. Let's let G be a non-trivial P group, finite P group, of course, and N be a normal subgroup of G that's non-trivial, so a non-trivial normal subgroup. Then the intersection of N and the center is not trivial. So just to check, if you take N to be equal to the center, which we know is a normal subgroup, then you get exactly the statement from before, that the center is not trivial. Okay, what does this say? Every non-trivial normal subgroup meets the center non-trivially. So you can always take the center and intersect it with other subgroups and see what kind of subgroups you get out of those intersections. And the point is that if you intersect it with another normal subgroup, you're getting the intersection that has to be non-trivial. Okay, we just have to pick the right action in the fixed point congruence. So let's let G act on N by conjugation. All right, so why is that actually a group action? Well, N is a normal subgroup, so Gn G inverse is equal to N for all G and G. So if you take an element X in N, Gx G inverse is going to be some other element in N. So for each fixed G, we're getting a permutation of N, the elements of N, in a way that is compatible with the group operation. Okay, so what are the fixed points of this action? They're exactly the elements of N intersect the center of G. So now the fixed point congruence tells us that the size of this intersection, which is the number of fixed points, is 0 mod P, because the set that we're acting on, N, well, it's a subgroup of a finite P group. So that means that it is 0 mod P. So we're getting the size of this number of fixed points is 0 mod P. And since the identity is always in N intersect the center, we have something that's 0 mod p and it's at least 1, so it's at least